So first of all, I'd like to thank Professor Jin Wang giving me an opportunity to come to Peking University. Actually, this is my third time coming to Peking University. And actually, because of the COVID, I could not go abroad for the past 3 years. But recently, I'm free to go abroad. So my name is, I'm Yuji Matsuda from Department of Physics, Kyoto University. So this is a symbol of Kyoto, the pagoda of Kyoto, and this is a symbol of a character. Maybe you understand what this means. But actually, as you know, Kyoto has been a capital of Japan for more than 1,100 years. I'm sorry, longer than Beijing. Okay, so today I'd like to talk about the Majorana fermion in a quantum spin liquid. So I'd like to talk about the insulator. Okay. So let me first mention my collaborators. This work mainly has been done by Kazahara and Setsugu and Asaba and Kosaka in collaboration with Takashi Bauchi's group, University of Tokyo, and all crystals grown by Tanaka, Tokyo Institute of Technology, and Nasu, Motome, Hike, Traverse Moon provided us many important theoretical suggestions. Okay, in my talk, I'd like to start with explaining Kita quantum spin liquid, which is the main subject of my talk. Then I talk about half-integer quantum thermal Hall effect in alpha ruthenium Cl3, which I mainly discuss today. After that, I will discuss topological properties of alpha ruthenium Cl3, focusing on planar thermal Hall effect, and evidence for Dirac cone and Majorana gap. Then I will discuss origin of the thermal Hall effect, fermionic or bosonic. This has been a very highly controversial issue recently. I will show the conclusive evidence of the fermions. Yeah, if time allows, I'd like to talk about our recent SCM measurement of monolayer alpha and beta ruthenium Cl3. The result of beta ruthenium 3 has been published 1 week ago. Okay, let me start with explaining quantum spin liquid. So, quantum liquid is a system in which the quantum fluctuations melt the long-range order. So they remain, the most famous example of the quantum liquid is helium-3 and helium-4. So they remain liquid even at t equals 0. So quantum spin liquid is a spin analog of quantum liquid. Actually, the no freezing of spin occurs even at t equals 0. So quantum spin liquid have been widely discussed theoretically, but no real systems. It was only recently that several candidate materials have been found. There are several, three important requirements for the quantum spin liquid. First is the absence of magnetic long-range order. Actually, the correlation function decays to 0 as the distance goes to infinity. Second is the absence of any simple spontaneous broken symmetries, such as spin rotational symmetry or lattice symmetries. Very recently, the important concept has come into play. It is fractionalized excitations and topological order. So they appear as a result of huge quantum mechanical entanglement in the ground state. This is a really new important concept of quantum spin liquid. So why study quantum spin liquid? There are several reasons. So they could be as interesting as the fractional quantum Hall effect, according to Leon Barents. Then doping quantum spin liquid may be a path to new topological superconductors. Third is possibly it provides a path to topologically protected quantum computing. Okay, I'll discuss this point later. So it is generally believed in the dimension 2 or 3, the geometrical fluctuations are required to stabilize the quantum spin liquid. The most famous example of the geometrical fluctuation is triangular and kagome and pyrochloride lattice. They always have a strong frustration effect. And many exotic particles, like spinons and bosons and monopoles and photons, have been proposed. Yeah. So we have been studying quantum spin rigid by the thermal transport properties. Let me explain why. Because the fractionalized excitations are charge neutral, because the system is insulator, then they do not carry the charge, but they may carry the heat. So if you heat up one side of the crystal, the temperature gradient may appear because the quasi-particle can carry the heat. Then the temperature difference may appear along the longitudinal directions. So this is a thermal conductivity. So thermal conductivity can sensibly probe low energy itinerant excitations. They cannot measure localized excitations. Okay, let me show you one example. Here's one example of the thermal conductivity of triangular lattice. This organic compound, DMIT. This material has a triangular lattice, and exchange constant is nearly 200 Kelvin. Nevertheless, no magnetic order occurs down to 20 millikelvin, which is nearly 10,000ths of J. And the specific heat shows our gapless excitations, gamma, are similar to metal. So here is the result of the thermal conductivity, kappa over T, plotted as a function of T squared. So, okay, so this is the non-magnetic reference. This material has no charge order, but very similar crystal structure. So this difference comes from the spin excitations. The most important point is here, there is a residual thermal conductivity, kappa over T, at zero temperature limit. So zero kappa over T is a signature of metal. But again, I want to emphasize, this is insulator. So this indicates gapless itinerant excitations are present in this material. So very recently, similar behavior, similar finite residual resistivity has been observed in this organic material, tantalum S2, and this material by Chinese group. So they discuss this finite residual thermal conductivity in terms of fermi surface of spinon excitation. So, as I mentioned, the thermal temperature gradient appears in the longitudinal directions. But if we apply the magnetic field, temperature gradient may appear in the transverse directions. So this is a thermal analog of the electric Hall effect. So this is a thermal Hall conductivity. So why the thermal Hall conductivity is important? This may capture non-trivial Berry phase of quasi-particles. So it provides access to various topological excitations. This is why the thermal Hall conductivity is a powerful means to probe the topological excitations in the quantum spin rigid. Okay, so today I will discuss the system of honeycomb lattice. So honeycomb lattice does not have geometrical fluctuations, but this honeycomb lattice can have different types of fluctuations. So today I discuss Kitaev quantum spin rigid. So Kitaev model discuss spin 1/2 on honeycomb lattice with 3 equivalent bonds. The Hamiltonian is given by these equations, and as shown by this figure, the Kitaev interaction is bond dependent Ising-like. So each favors different direction of x and y and z, like this. So if the spins are aligned along the z-axis, the bond energies along x and y-axis are not lowered. As a result, the spin cannot satisfy 3 different configurations simultaneously. So this leads to exchange frustrations. Because of this exchange frustration, a system cannot show the ordering. down to t equals 0. But this is a Kitag spin rigid. So Kitag model, okay. Okay, why is a Kitag quantum spin rigid interesting? One important point is the fractionalization. So fractionalization is a individual electron split into pieces. So in the fractional quantum Hall effect, fractionalization of charge occurs. But in the Kitag quantum spin rigid, fractionalization of electron spin occurs. As a result, topological order with emergent exotic particle appears. So emergent quasi-particles are Majorana fermions and non-abelian anyons. So it is very similar to px plus IPR superconductor and 5-half fractional quantum Hall state. Majorana fermion is a particle which is its own particles. Actually, neutrino is a candidate of Majorana fermions, and 1 Majorana corresponds to half of electrons. So this is very important point for the thermal Hall effect. Let me discuss abelian anyons. Anyons. So needless to say, if you exchange two particles, the wave function picks up the phase theta. So as you know, in case of boson, theta equals 0, and fermion, theta equals pi. So let me explain why this is 0 or pi. So two successive exchange correspond to a circulation of one particle winding one around the other, like this. This operation corresponds to two successive exchange. So in case of 3D, let me consider three passes, C0, C1, and C2. So C0, we do not observe. We do not move the particle. So C0, C1, the particle move like this, and C2 particle move like this. So all these C0, C1, and C2 are identical. So because by lifting this path, we can it is possible to continuously deform the loop C1 and C2. This is why in the 3D, all paths are identical. So on the other hand, in 2D, obviously the C0 to C1 is identical, but C2, this path, is topologically distinct from C1 and C0, because we cannot deform the loop of C2. Therefore, in this case, anyons, neither bosons nor fermions can exist. Okay, so anyon exists in 2D. So there are two types of anyon. So the theta can take any values, and a different set of particle appears for every theta, like this. So this particle is called abelian anyon. However, the exchange operation may be non-trivial operations. So the exchange can be written by unitary matrix. So in this case, exchange yields a new quantum mechanical state. So such a particle is called non-abelian anyon. So this is important because the exchange of non-abelian anyon is a quantum gating operation. Therefore, this is a non-abelian anyon is a key particle for topological quantum computation. As you know, the topological quantum computation, we need not error correction. The Kitag quantum spin rigid, there are two ground states, gapless and gapped, depending on the parameter. So both of them have a exactly solvable quantum spin rigid ground state. So when this J is very anisotropic, the gapped spin rigid which has abelian anyon appears. So this state it corresponds to toric code state, which is introduced in the context of topological quantum error correcting code. But when the gap is isotropic, gapless quantum spin rigid state appears in zero field. This state has non-abelian anyons. So today I will discuss the material close to this state. So the Kitaev introduced Kitaev described spin 1/2 by two fermions, and the two fermions are decomposed into Majorana fermions. Three Majorana fermions. All Majorana fermions are anti-commuting, and they are own their own particles. So so three of Majorana fermions are localized, and one is itinerant. So this interacting spin can be written by this. So I skip the details of mathematics, and by introducing this Majorana fermions, this very strongly interacting spin can be written by non-interacting particle of itinerant Majorana C. Okay, so excitation from the Kitaev spin ligand is described by Plaquet operator written by this one. So the Plaquet operator commute with Hamiltonian, and the WP can be taken as plus minus 1. Okay, I skip the detailed argument. So the ground state, the all Plaquet has plus 1. This is a ground state. But the excited state is WP become minus 1. Such a state is called D2 flux boson excitations. So boson has an energy gap. Okay, simply speaking, the spin 1/2 is written by itinerant Majorana and localized Majorana, and localized Majorana forms a boson or a gauge flux. This is excitation, and energy gap. This boson has energy gap. It's nearly 10% of Kitaev interactions. So this is a schematic figure of Kitaev spin ligand. So at high temperature, the system is paramagnetic regions. And below the Kitaev interactions, spin fractionalization occurs, and itinerant Majorana spins are fractionalized into itinerant Majorana and G2 flux, like this. And at very low temperature, this G2 flux with gap disappears, and the itinerant Majorana move around the honeycomb lattice. And this is a truly quantum spin liquid state. So this fermion is moving in the honeycomb lattice is very similar to graphene. So as expected, the excitation has Dirac cone. This is same as graphene. But the difference between the graphene and the Kitaev quantum spin liquid is the response to magnetic field. So if we apply the magnetic field, the third perturbation of Z1 term give rise to the second nearest neighbor hopping Majorana, and actually this open, the gap opening occurs at the Dirac point. The situation is very similar to quantum Hall effect without random level proposed by Haldane, and gap appears here. So this is very different from the graphene, and in this state, system becomes topological, and Majorana-Chan insulator characterized by Chan number pairs, and in this state, the chiral edge current of Majorana appears. So let me compare this result with with integer quantum Hall effect. So as you know, in integer quantum Hall state, sigma xy is quantized in units of this quantum conductance. At the same time, it is quantized in the unit of kappa xy. Thermal Hall effect is thermal conductance is quantized in units of quantum thermal Hall conductance. So this charge and thermal current is carried by chiral edge current of electrons. In the Kitaev spin ligand, the chiral edge current of Majorana fermion carries the heat. So but important point is kappa xy is half of K0, which is half of mu equal 1 quantum Hall state. This is half because degree of Majorana fermion is half of electrons. So in other words, if we observe this half integer thermal Hall effect, this is a direct evidence of Majorana fermion. As I will discuss later, this is also direct evidence of the presence of non-abelian anion. The Kitaev model is just a mathematical model, but Jacqueline and Caroline discuss the Kitayef interaction in materials. So they consider how field d5 orbital in the presence of octahedral crystal field. Then the orbital split TEG and T2G. And in the presence of strong spin orbit coupling, how field J equal 1/2 state appears. So in the presence of strong electron correlation, J equal 1/2 Moto insulating state appears. Then this state is written by, described by isospin, and which is identical X and Y and Z direction. And when the crystal shares, has a edge sharing octahedra, the interaction, indirect hopping or super exchange from this path and this path exactly cancels because of the interference effect. Then the Heisenberg interaction becomes Ising. So because of this isospin structure, if the crystal structure is like this, the Kitayef interaction is realized. So actually, there are several candidate materials of the Kitayef interaction. So mainly iridium compound and ruthenium compound. So today, I mainly discuss this alpha ruthenium Cl3. So this material is a prime candidate for the Kitayef quantum spin ligand. This material has a strong, is a strong spin orbit coupled J equal 1/2 Moto insulator. So this material has a honeycomb lattice of spin 1/2 ruthenium. But actually, this material has a non-Kitayef term, such as Heisenberg and off-diagonal term. But many experiments show that the Kitayef interaction dominates among the magnetic interactions. So because of the non-Kitayef interactions, this material shows an antiferromatic order with zigzag spin structure at T equal 9.5 Kelvin. Also, this material shows an antiferromatic order. There are several signatures of spin fractionalization. The first is the specific heat. Specific heat shows a magnetic part of the specific heat shows a broad peak as the temperature corresponds to Kitayef interactions, and the nearly half of R log 2 entropy release occurs at the end point of this peak. So this peak structure has been suggested to be a signature of fractionalization. The second is Raman scattering. The Raman observes the broad magnetic continuum excitations, and unintegrated Raman intensity decreases with temperature, but it increases at low temperatures. So this is temperature dependence is totally inconsistent with bosonic magnon. So this is consistent with fermion. So this is another evidence of fractionalization. I mean, the fermion appears. Magnon is boson. Okay. The third evidence has been given by neutron. The neutron experiment has been done by several groups, and neutron observes the magnetic continuum at the gamma point, and this horn-like structure this point. So these are consistent with these are in good agreement with the excitation in the Kitayef quantum spin ligand. Okay, now let me discuss half-integer quantum thermal Hall effect in this material. So in this material, antiferromatic order occurs at 7.5 Kelvin. But if we apply the magnetic field parallel to AB plane, this antiferromatic order is suppressed, and the paramagnetic state, we often call the field-induced quantum disorder state, appears. So the most important question is what is this paramagnetic state? So is this a simple paramagnetic state or some quantum spin ligand state? So that's the most important point. So to clarify this point, we measure the thermal Hall effect in tilted magnetic field. So in this case, the magnetic field parallel to AB plane suppresses the order, magnetic order. So here is a field dependence of thermal Hall effect, kappa xy divided by temperature as a function of magnetic field. The magnetic field is applied 45 degrees tilted from the AB plane. In the This antiparametric state, thermal Hall effect is very small. But upon entering the spin rigid state, thermal Hall effect is strongly enhanced. There is an extended figure. So we observe the plateau of the thermal Hall effect. And at high temperature, this disappears. But the thermal Hall conductivity per 2D layers, actually we divided by number of the layers. So this is very close to the half integer value. So this is close to the half of K0. K0 is a quantum thermal conductance. So this is evidence of the Majorana edge current. Okay, according to conformal field theory, the kappa xy is written by CK0. C is the central charge. So if the concentration occurs with C less than unity, this is a direct evidence of non-abelian anyon. But I don't know where the quantum conformal field theory. But in case of Kita quantum spin rigid, non-abelian anyon is a composite particle of the Z2 gauge flux and the Majorana fermion. So actually the Majorana fermion is captured by Z2 gauge flux and the Majorana zero mode pairs. So this composite particle is a non-abelian anyon. So the half of quantized thermal Hall conductance is a direct evidence of this non-abelian anyon. Okay, only important question is reproducibility.
Is there any estimate for the magnitude of the carbon?
Actually, there are many experiments using resonant X-ray and neutron, and they can determine the Kita interaction directly.
So, what the magnitude of the number?
Oh, okay. So. Yeah, number is nearly 50 Kelvin to some measurements show the 50 Kelvin, but some measurements show 100 Kelvin, 5 millieV or 10 millieV.
And also, you only have a decoupling.
So this one?
No, in the in the component, you only.
Sorry. Sorry. This IG. Please forget this whole Z. Okay. Maybe this print. Forget Z. But this. Okay. Okay. Yeah. We see sigma. X.
So, since in that experiment you observe this color is half quantized.
Yeah.
10 Tesla.
10
Tesla should be about maybe the Riemann energy is about maybe
10 Kelvin. 10 K.
10 K is maybe 1 millimeter.
Yeah.
1 millimeter.
Yeah.
So it's just maybe 0.2 K.
Yeah. Okay. But
so just I think in this region maybe this speed the non-real phase. I think the non-real phase could be stable as maybe.
Yeah. Okay.
Yeah. From 1 K like that.
Yeah. Okay. Important for energy is the Majorana gap. Okay. Majorana gap is order of 20 Kelvin or 15 or 10 Kelvin. Sorry, 20 Kelvin. Then if the Zeeman energy exceed the Majorana gap, we cannot expect quantization. Yeah, okay, it depends on the magnetic field, but order of 10 Kelvin to 20.
For an ideal
Yeah, but actually there is no prediction of the which magnetic field quantization occurs.
Yeah, the magnitude for K is not fast, maybe more larger.
Yeah, it might be larger.
And also, this is not an ideal that the model system because of technical problems and also the couplings.
Oh.
We have more couplings. The other couplings in general may suppress or maybe reduce the gap. I'm not sure. Maybe.
Yeah. but maybe I will discuss the magnitude gap later. Okay. Okay. We measure several. Okay. Until now, the 5 groups all the world measure the thermal Hall effect. Actually, this kind of concentration plateau has been reported 5 years ago. In the past 5 years, 5 or 6 groups measure the thermal Hall effect, and quantum plateau has been reported by University of Tokyo and Max Planck group, crystal growth Bridgman method. But some material does not show the concentration. They show the plateau but no concentration by Bridgman method. So very recently, the Oak Ridge group measures the crystal grown by CVT, chemical vapor transport. Actually, they report the plateau shown here, but the plateau value is nearly 75% of how quantized. I think this may be due to some kind of a stacking fault. But anyway.
This is all per layer?
Yeah, per layer, yes, per layer. They divided by number of the layers.
But if it's quite thick, how do they count, for example, CVT, how do they count how many layers are there?
How to account the, sorry?
Yeah, layer.
Layers. But we know the lattice constant. And we can measure the thickness very accurately by using recent electron microscope. So the Princeton group reported 2 years ago no plateau and last year, so no plateau and no concentration.
Also, you can make sure that for different layers, the thermal, the temperature gradient should be uniform.
Yeah.
If for different layers, the temperature gradient is different.
Yeah, but we are but we are using a very thin crystal.
Normally,
Whereas 10 micrometer to 500 micrometer, and so the temperature gradient is quite uniform. Okay. We have 0.5 to 1 millimeter. The thermal conductivity, exact value. That's okay. Thermal Hall effect is extremely small. It's nearly 0.2% compared to kappa XX. Because kappa XX contains phonon, large phonon contribution, but the kappa XY does not contain the phonon contribution. The phonon contribution dominates in this material. Therefore, the value of kappa XY is 0.1% or 0.2% of kappa XX. That's why the experiment is extremely difficult.
How to make sure the direction is exactly
but direction is not so problem because we apply multiplicator, right? Yeah, like this.
I mean the alignment of the contact. Then it seems to matter.
Just watch the sample. Just watch the contact.
Micro fabrication for the contact.
No, we do it by hand. By hand. Okay. Yeah, we try the micro fabrication.
What's the error?
Okay. Yeah, error bar is plus minus 5%. Error bar comes from the geometrical effect, the size of the contact.
What's the difference between this Y and the same group?
This one?
Yeah, this one is
Same group. Same our group, but different. Different. Yeah, that's an important question. But that's a problem. Okay. Yeah. But actually, in these materials, the absolute value of kappa XX is small. That means it contains many impurities.
Or many impurities.
Yeah. I think so.
Somehow growth methods are same. Originally.
Yeah. Yeah. But they are different batch. Different batch. Yeah, different batches. Yeah.
Okay. It should be slightly different to disorders, right? Impurity.
Yeah.
It is a quantized chain number.
Yeah. But anyway, okay, let's go. So here's a temperature dependence of the quantized value. So the condensation occurs in the limited temperature range from 3K to 7 Kelvin. So at low temperature, it deviates from the quantized value. So this has been explained by Archibald and Leon Barents. And actually, at low temperatures, the decoupling of phonon and edge current occurs. Actually,
There's another question. Can you go back to the previous slide? Yeah, so when you change the temperature, you change the matter field.
Yeah.
So from the forward phase to maybe the trivial phase.
Yeah, yeah.
So you just have a slow review from the conservation to zero.
Yeah.
But from the topological to the trigger, you have a gap closing one.
Yeah, okay.
Yeah, you should have a gap closing form.
Yeah, that's okay. This again the controversial. There is another phase transition here. Phase transition of the quantum spinning occur here. Yeah, we have some evidence of some phase transition at 11 Tesla or 12 Tesla. Nobody knows. That's a very it's a very important point. Nobody knows what kind of phase transition occurs at this point. But there might be phase transition. There must be. Okay, so the quantization occurs in the limited field range, and decoupling occurs. Decoupling occurs because at low temperatures, the phonon mean-free paths become comparable to the size, crystal size. In that case, we cannot determine kappa XY accurately. But actually, the phonon mean-free paths become comparable to the sample size at nearly 3 Kelvin. And at a high temperature, deviation again occurs. This has been proposed by the effect of boson. Boson are excited. Then the condensation is violated. Okay, now I'd like to talk about the topological properties of this material. I first discuss a planar thermal Hall effect. Where topological Chern number of Kita spin liquid is determined by this one equations. And this is a field component with respect to the spin axis. So I'd like to emphasize this spin axis is determined by spin-weight interactions. So it is different from the crystal axis. So the crystal axis is here A, B, and C, and X and Y and SY, XX, and SZ is a spin axis. So different from the crystal axis. So here is a Chern number in the AC plane. So as you know, the sign change occurs nearly 35 degrees tilted from C axis. So this is totally different from the conventional Hall effect. Because in the conventional Hall effect, sign change occurs at the multiple field this direction and this directions. So the important point is this one. Planar thermal Hall effect appears. Okay, actually, definition of planar Hall effect is really confusing. But in your definition, of the planar thermal Hall effect is the transferred electric field appears even when the thermal so electric current and magnetic field is applied in the plane, and this electric field is a auto function of H. This is our definition of planar Hall effect. Maybe the spintronics people are using a different definition of planar thermal Hall effect, but we use a definition of planar thermal Hall effect by this one. Then I'd like to draw your attention. The Chern number is finite, even in the magnetic field applied to AB plane. So this means emergence of planar thermal Hall effect. This means even if we apply the thermal current and magnetic field within the AB plane, the finite temperature gradient appears in the longitudinal directions. And this temperature gradient is an auto function of H. So this is our definition of planar thermal Hall effect. So this planar thermal effect is a purely topological effect. Because in the classical Hall effect, we cannot expect this kind of Hall effect. Okay, here's a magnetic field, Chern number in the AB plane, in the plane. So if you have the magnetic field applied, minus A axis, Chern number is plus, and the sum of the Hall field is plus, and on the axis, channel number is minus. And here, if I have a magnetic field, the armature directions, channel number is 0. So we cannot expect any sum of Hall field. This comes from the symmetry. So the important point is this one. So Hall sign change occurs when the magnetic field is rotated across the b-axis. So this indicates the emergence of angle rotation-induced topological phase transition in this material. So this is a stringent test for the Kitaev quantum spin liquid. Let me show you our result. We apply the thermal current in the plane and the magnetic field in the plane. So in the magnetic field applied parallel to a-axis, minus a-axis, we observe the planar thermal Hall effect, and it is quantized. It is very close to quantized value, and it shows the plateau. So then we apply the magnetic field parallel to b-axis. We never observe the thermal Hall effect. It's 0. So these are consistent with the Majorana band of Kitaev's quantum spin liquid. Okay. Very recently, we have measured the sign of planar thermal Hall effect. We measure the thermal Hall effect in magnetic field rotating within the AB plane across the b-axis. So also the quantization does not occur because the gap is very small, the b-axis. But we clearly observe the sign change of the thermal Hall effect when the magnetic field is crossing b-axis. This is indicates the planar thermal Hall effect change sign when field is rotated across b-axis. This is evidence for angle rotation-induced topological phase transition. This is consistent with the Majorana band.
So your magnetic field is a vector magnet, or you
we rotate it. Yeah, because we need to magnetic field nearly 10 Tesla, so we cannot use a vector magnet. Okay, so let me summarize the reproducibility of thermal Hall effect. Actually, in the condensed matter experiment, most important issue is reproducibility. If someone observes something, but if other group could not observe something, people become very skeptical about the data. So until now, the 5 group measures the field dependence of the thermal Hall effect. So Kyoto and Tokyo and Max Planck, Stuttgart, observe the plateau and half quantized value. And the sign of kappa xy is consistent with the Kitaev model. And Oak Ridge also observes the plateau, but this value is 75% of half quantized value. But the sign of kappa xy is consistent with Kitaev. And the planar thermal Hall effect has been observed by our group and Princeton group and Oak Ridge group. But Princeton group and Oak Ridge group. But the Princeton group never observed the plateau and half integer quantum Hall effect. So instead, this is their interpretation. They claim the half quantized thermal Hall effect is accidental. Also, it's very hard to believe that it's accidental. But anyway, they claim the origin of the thermal Hall effect is boson, not fermion. And they predict the topological bosonic edge excitations coming from the topological magnon, and the magnon gap is order of 1 millieV. So and very recently, Yonbak Kim's Toronto University group claims the topological magnon, even the topological magnon, the sign of kappa xy can be explained in specific parameter range. Therefore, the sign of the thermal Hall effect is not a smoking gun of the Kitaev model. But moreover, Princeton group reports oscillating thermal conductivity like this. So they claim this is a quantum oscillation of fermionic quasi-particles. But Max Planck group and Louis Taillefer's group, Canada suggest this oscillation is not come from the quantum oscillation, but come from the local magnetic order. But anyway, to clarify this point, this is quite controversial. To clarify this point, we need a very clean crystal. Actually, recently the visiting professor in Xing, who got a PhD at your laboratory, she is planning to measure kappa XY and kappa XY on ultra clean alpha ruthenium Shell3. Actually, we have succeeded to grow ultra clean alpha ruthenium Shell3 by using sublimation technique. Actually, in our method, no signature of magnetic order and specific jump at the nail transition nail order is very sharp, very large. Okay, coming back to the origin of thermal Hall effect. There are two scenarios, Majorana fermion and topological magnon, in other words, fermion or a boson. So the Chan number can be same. But the main difference here is the if the magnetic field applies the b-axis, in the Majorana fermion model, it's gapless, and the Dirac cone preserves in the field directions. So for Majorana case, the gap closes at the magnetic parallel to b-axis, but in the magnon case, the gap opens. So specific measurement can distinguish two scenarios. So recently, next let me discuss thermodynamic evidence of Dirac cone and Majorana gap. The measurement has been done by Takashi Baguchi's group, University of Tokyo. To measure the specific heat from very tiny crystal, we used long radiation calorimetry technique. In this technique, the heat capacity of agenda is less than 0.1% of typical PPMS. So we can determine the specific heat very accurately, even on the very tiny single crystal. So we use a two-axial rotator in dilution refrigerator, so that we can apply the magnetic field very accurately along the b-axis. So here is the angular dependence of the specific heat. Then, let me show you our result. First, we apply the magnetic field parallel to b-axis. So Dirac cone is predicted in this geometry in Majorana model. So in this plot, C over T square is plotted as a function of T. So I'd like to emphasize, we do not subtract phonon. But actually, once we do not want to subtract the phonon, because once we subtract the phonon contribution, some people complain, how did you calculate the phonon contribution? This always occurs in the community of specific heat. So this is a rotator. Okay. Now the important point is that we have finite intercept at t equals 0. So this means that specific heat is proportional to t squared. So this is observed on the wide field range. And actually, we measure the specific heat down to 0.2 Kelvin. This corresponds to 0.2% of Kita interaction. We measure very low temperature. Then we also rotate the magnetic field, tilt the magnetic field 1.5 degree, plus minus 1.5 degree tilted from the b-axis. So as you see, the t-square term disappears when magnetic field is slightly away from the b-axis. So we estimate the gap. So the gap closing occurs at θ equals 0. So if the magnetic field tilted only 1.5 degree, the gap opens. So these are totally incompatible with 2D or 3 magnon or phonons. And this result definitely indicates the linear dispersion showing the presence of Dirac cone. So this topological magnon scenario can be excluded. In case of Dirac cone, yeah, but actually, as I mentioned, in case of Dirac cone, kappa XY is proportional to t cubed. It's very hard to distinguish from phonon. Schottky term. Unfortunately, we never observe Schottky term down to 0.2 Kelvin. The Schottky term is very small in this material. But if you go down to 100 millikelvin, Schottky term may appear. Okay, we apply the magnetic field parallel to the axis. Then, in this case, we have the intercept is 0. So at low temperature, specific heat shows a T cubed dependence. So this comes from the phonon. So if we subtract the phonon contribution, we observe the exponential behavior. So gap amplitude is order of it depends on the magnetic field, but order of 10 Kelvin. So this gap is proportional to h cubed. So this is consistent with Majorana gap. Okay, summarizing the result of the gap Majorana specific heat. If the magnetic field is applied parallel to the a-axis, we observe the gapped behavior. So gap opens the bulk, and this gap is proportional to h cubed. So this is consistent Majorana gap. So this means a gap opening in the bulk. But looking at the thermal Hall effect, we observe the final thermal Hall effect. So this means a thermal current flow at the surface or edge. But this is quantized. This thermal current flow at the edge. So this is a kind of bulk edge correspondence in this material. But if we apply the magnetic field parallel to b-axis, so Dirac cone preserved. So there are no Majorana gap in the bulk. So in this case, we never observe the thermal Hall effect. So consistent with the Kitaev model. Okay, finally, let me discuss the origin of the thermal Hall effect, fermionic or the bosonic. So some people are not still convinced by quantized kappa xy. So especially some theorists do not believe some theorists are always skeptical of the experiment. So some people say that I don't believe something. But anyway, some people are not still convinced by quantized kappa xy. Reason is we cannot determine kappa xy accurately. Some people say, okay, this is not exactly quantized, but this is thermal measurement. So we have error about plus minus 5%. Second is deviation from the quantized value occurs at low temperature, possibly due to the decoupling of phonon and edge current. Third point is we cannot fully explain the sample dependence, in particular gross method difference. So we need a new approach to tackle the quantized thermal Hall issue without relying on the magnitude of kappa xy. So actually, I'd like to show you, we can conclude the quantized kappa xy without showing the quantized thermal Hall conductivity. Let me discuss this. Okay, I'd like to remind you two experiments. The magnetic field rotating across the b-axis. The specific heat, we measure the specific heat rotating along the in the plane. The magnetic field rotating with the plane across the b-axis. So in the b-axis, we observe the Majorana Dirac cone. But if we tilt it slightly, the gap opening occurs, and gap closing occurs at the magnetic field parallel to b-axis. Okay. Second point is the planar thermal Hall effect. As I mentioned, planar thermal Hall effect changes the sign when the magnetic field, when in plane magnetic field across the b-axis. So the Hall sign change occurs at parallel to b-axis. In other words, topological phase transition occurs at the magnetic field parallel to b-axis. So two distinctive phenomena features are observed concurrently at the magnetic field parallel to b-axis. So I would like to emphasize these are totally different experiments. These are specific heat, measure bulk, and planar thermal effect, measure the surface. Okay, let me consider two cases, two scenarios, fermion case and the boson case. So in fermion case, the topological band is above and below the Fermi energy, because fermion always have Fermi energy. So when the thermal Hall sign change occurs and band crossing occurs, but a band crossing should occur at the Fermi energy. So the sign change of kappa xy is always accompanied by gap closing for fermion case. But this is quite a general argument. So on the bosonic case, the topological band is always exists on the finite energy. So when the sign change occurs, the band crossing occurs. But this band is always a gap. So the gap is always finite, and the sign change is not related to the gap closing. So I'd like to remind you that in alpha ruthenium shell 3, gap closing and topological phase transition concurrently occurs at H parity B axis. So this totally inconsistent of the boson is strong support of the fermion. So this provides conclusive evidence for
in fact, for the boson, you undergo this gap closing, and before closing and after closing, the lower band is different. And in the final temperature, so this band will be excited. You have a thermal distribution for the lower band for the magma. So this bulk of this magma will also contribute to the thermal magma.
Yeah. So okay, my question is okay. Sign change.
Right.
Sign change is gap closing.
Yeah, this gap is open at the final energy, is not at the zero energy. That's true.
Yeah.
I agree with this picture.
Yeah.
But I mean, at the final temperature, so then the band, the bulk is populated with magnets. The bulk.
Yeah, but that magnon has gap.
It's gap, but you can still have the population, depending on how large is this gap.
Oh, it's also 1 milli eV, 10 Kelvin. Yeah. Okay. The calculation shows that this gap is order of 1 milli eV, order of 10 Kelvin.
I mean, before this gap, mostly this lower band is occupied or is populated. So with the number, maybe with electrical culture, which contributes to a electrical thermal conductance. And after the band gap, after the gap closing, on the right hand side, the lower band is corresponding to the number is plus 1. So the culture will be positive mostly. In the other case, the thermal conductance for the magnets will also become to be positive. So you still have the sign change, but the magnitude will be different. You should also have the sign change for the.
Okay. Okay. In magnon case or bosonic case, we can explain the sign change. But sign change occurs. The gap is always finite. But in this gap close. Yeah. Then what we observe is the gap closing and sign change occurs simultaneously. Yeah, this is quite a general argument, right? Then our result is provide concrete evidence of the fermionic origin, because it's impossible to explain this by our result by magnon. Yeah, as a special case shows, gap closing. Right? Yeah, gap closing occurs at C equals 0, and at the same time sign change occurs. So my point is, it's impossible to explain this behavior by boson.
That gap is detected by other way, by the different method to measure the gap. If you not measure the gap from the bottom out, you just measure the.
Yeah, but this gap is measured by specific heat.
Measured by what?
By specific heat, okay. This is a measurement of specific heat. So thermodynamic measurement. Then it closes the gap. This is a thermal hole. Okay. Then our conclusion is this is a fermion. Yeah, this is a quite general argument. So we can conclude that. So that if we accept the fermion, the thermal hole conductance must be quantized at T equals 0 because of this band. So this is our conclusion of the quantizer Hall effect. is realized in this system. Okay, if you compare the integer quantum hole and anomalous hole, the origin of the electrons and origin of the cyclotron gap and band gap, the fraction of quantum hole, the particle is the composite of fermions, and Coulomb gap opens, and fractionation of charge occurs, and non-abelian appears, and also abelian and non-abelian appears. But in the Kirchhoff spin limit, the derived particle is Majorana, and the gap is the Majorana gap, and the fractionalized spin appears, and non-abelian appears. So this is a different type of quantum sum of quantum Hall effect. Okay, finally, let me discuss a very recent result of STM studies of monolayer, alpha and beta ruthenium shell 3. Okay, this is a theoretical proposal. Some theories predict we can detect non-abelian anion on monolayer alpha ruthenium shell 3. But actually, recently we grow alpha ruthenium shell 3 on graphite, HOPG. And these are the STM result. We grow on pulse deposition. Actually, recently the Fudan University group have succeeded to grow monolayer ruthenium shell 3 by MB. They grow very nice monolayer ruthenium shell 3. But actually, we tried to grow monolayer ruthenium shell 3 by MB. But we never succeeded. Actually, once we evaporate ruthenium shell 3, it decomposes into ruthenium and Cl2. I thought some group of Fudan. Yeah. But maybe they have some big secret, which is not written in the paper. But anyway, we spent more than 3 months, but we never succeeded. So maybe in this case, we are 400 C. Yeah. And also, some group measure the growth of monolayer alpha ruthenium shell by the Scotch tape method, by But anyway, so this is consistent with this atomic image is consistent with ruthenium shell 3, and we observe a Mott gap nearly 1 eV. But actually, we apply the magnetic field and we change the temperature, but nothing happens. But I would like to switch the subject. But during the experiment, we observe this ordered pattern of atomic wire. Rather surprisingly, okay, so this atomic wire can be grown on graphene. Not only HOPG, but also we can succeed to grow graphene on silicon carbide. So after this experiment, we found this wire is not alpha ruthenium shell 3, but beta ruthenium shell 3. This is a spin-orbit-motor insulator. Actually, this wire length is very long. Look this data. This one. This all.
Yeah. Wire?
Yeah, this is a wire. Continuous wire.
Is it some kind of order or something?
Sorry.
Order or what?
Oh yeah, yeah, ordered. Ordered is there. As you see, it's a. Yeah, sorry.
Why is the insulator?
Yeah, insulator.
So it's not the boundary, not boundary.
Yeah, not boundary. Yeah. But that is the wire width is less than 3 nanometer, but the length is more than 3 micrometer. But recently we found the length is more than 10 micrometer. This is really the nanowire. Okay. Oh, okay. We can control the by changing the temperature and the evaporation rate. We can control the width. Then the origin of this self-integrated quantum wire. The size of the nanowire is order of 2 nanometer. So we can grow on the graphene. So okay, I skip the detailed origin, but this is very similar to tropical fish. But okay, but I don't know this strike pattern of tropical fish has been discussed in terms of the Turing pattern. Turing pattern, and this is a biological Turing pattern. So we believe this formation of this atomic wire is due to some non-equilibrium reaction diffusion process. We can show it by equations, but this we call atomic Turing pattern is realized. So the size is more than 1 million times smaller. So this is first experimental evidence of the atomic Turing pattern. Then the future prospect is actually we can grow this kind of atomically flat X junction and Y junction and this nanoring. So the beta ruthenium Cl3 is a spin orbital motor insulator. So but actually we don't know the detailed interaction of each spins of ruthenium Cl3. But if this is very close to Heisenberg, then we can realize Tomonaga lattice liquid. But if the actually recently some theorists mentioned the Ising-like interaction is realized in this system. So in this case, Majorana fermion may be excited in this Y junction here. And application of this wire, as I mentioned, we can grow it on graphene. So that if we use this atomic pattern by of lithographic mask, we can make graphene nanoribbon. Actually, we just propose a budget to make a graphene nanoribbon, but I'm not sure we will be able to grow graphene nanoribbon. But as you know, graphene nanoribbon is expected to have a high mobility and gap opening and multi-gauge state. So the present nanowires may be useful for graphene nanoribbon fabrication. Okay, let me summarize my talk. So we observe the half-integer quantum thermal Hall effect. This is a direct evidence for Majorana fermion and non-abelian anion. So we observed planar thermal Hall effect that is quantized. So we provided thermodynamic evidence for Dirac cone and Majorana gap in magnetic field. This is consistent with Majorana band of Kita quantum semi-liquid. And this we show the evidence for bulk edge correspondence. So we observe the angular rotation, induced topological transition, and gap closing occur concurrently at the magnetic field parallel to B-axis. This provides conclusive evidence for the fermionic origin of the thermal Hall effect. If we accept this conclusion, quantization must occur in this compound. So I show the result of the recent STM measurement on monolayer alpha and beta ruthenium Cl3. I show some evidence for atomic Turing pattern, which realizes a self-integrated atomic quantum wire of the order of 2 nanometer. Okay, thank you very much.